The Mercedes-Benz Stadium is not a simple structure. It's a complex system built layer by layer from the ground up. In this presentation, we will explain how this structure was actually constructed by following the construction process from the very bottom, the earth, upward. Starting with foundation planning based on site conditions, we will explore how each part is connected and why each construction method was selected, tracing the flow of the structural logic and construction strategy. The Mercedes-Benz Stadium site presented highly varied ground conditions with structural loads concentrated differently across specific zones. Because of this, a single foundation method was not sufficient to support the entire structure reliably. Instead, multiple foundation strategies such as shallow foundations, ground-improved bases, overcast piles, and drill piles were selectively applied based on soil profile and load characteristics of each zone. In particular, areas beneath mega columns were reinforced with high-strength foundation systems to ensure structural continuity and load stability. This adaptive approach allowed the foundation system to respond flexibly to real site conditions, providing a stable base for safely transferring structural loads into the ground. Due to the massive roof truss system and lateral structure, Mercedes-Benz Stadium concentrates structural and lateral loads on specific key points. To safely resist these forces, the project adopted a thick high-strength mat foundation and installed 19 mega columns instead of conventional spread footings. This foundation system was chosen to distribute large axial and moment forces, particularly around column zones where reinforcement density was increased to prevent localized failure and settlement. The mat foundation was designed with a thickness of approximately 2.5 meters and a concrete strength of 8,500 psi, significantly higher than standard structures. Construction began with the placement of bottom rubber in a dense grid. Rubber diameter was around 60 mm, spaced at 300 mm intervals. Standard 12-meter long rubber segments were lap spliced over approximately 2.5 meters. Less splicing around stress transferred without cutting the bars, and the connections were tied with steel wire. At column strip zones, where concentrated loads occur, extra bottom rubber was added, thicker and more closely spaced than in general zones. Next, top rubber was placed in a similar grid pattern above, completing the reinforcement cages. Above the mat, main vertical rubber for the mega columns were installed. To restrain these vertical bars, horizontal tie rubber was added. In lower portions of the columns where buckling is more likely, these ties were placed at tight 100 mm intervals for additional confinement. Instead of pouring the entire mega column at once, the structure was built in 3-meter vertical segments. This paced approach helped manage excessive hydration heats, concrete pressure during casting, and ensure safe, stable placement of large structure volumes. Each segment was cast after 24 to 48 hours of curing the lower portion. Mechanical couplers were used to connect vertical rubbers between segments, ensuring full stress continuity without reducing cross-sectional area. Before casting the next segments, bounding grouts was applied to the surface and vibration was used to eliminate voids and ensuring proper consolidation between layers. The mat foundation plays a critical role in distributing structural loads over a wide area, minimizing differential settlements and resisting both vertical and lateral forces. The mega columns support the massive roof trusses above and transfer all upper loads directly into the foundation and grounds. Through the use of high-strength materials, dense reinforcements, hydration heat management, and paste casting, this system successfully met the structure and construction challenges of the large-scale stadium. The slabs of the Mercedes-Benz Stadium have an average thickness of 305 mm, resulting in a self-weight of approximately 7.2 kN per square meter. If these loads are not adequately supported before the slab gains sufficient strength, there is a high risk of deflection, cracking, or even structural failure. To address this challenge, a temporary shoring system was used. This system supports the slab until it gains sufficient strength, and it is designed to withstand up to 290 kN per square meter of load. The primary components of the system are galvanized steel pipes with a diameter of 48.6 mm and a thickness of 3.2 mm, arranged at 1.2 meter intervals. These pipes are connected using couplers reinforced laterally with ledgers and braced diagonally to resist wind loads and vibrations. To handle the wide slab area and concentrated loads, steel I-beams or truss members are installed horizontally across the top of the vertical pipes. These elements help evenly distribute the load and serve as an accurate reference plane for installing the formwork and reinforcements. The plywood formwork placed above these beams includes pre-cut grooves, which are essential for shaping the integral slab and beam structure. In large slab areas, beams are necessary to resist bending. By forming reset channels in the formwork, concrete fills the deeper section, allowing beams to be monolically cast with the slab. In the beam areas, additional reinforcement is placed to resist bending moments. For the entire slab, double reinforcement is used, placing bars at both of the top and the bottom. Bottom bars resist tensile forces, while top bars handle compressive and flexural stresses, preventing cracking and deflection. Once the reinforcement is in place, concrete is poured and the vibrator is used to eliminate air pockets. Initial strength is typically reached in 7 days and the full design strength is achieved after 28 days. Once the slab reaches sufficient strength in support itself, the temporary shoring system is dismantled and reused in other sections. This modular system enables repeated use, achieving both construction efficiency and sustainability. The slab construction of the Mercedes-Benz Stadium reflects a thoughtful application of load management during construction, structural safety, and process continuity. Upon completion, the racker beams and precast seats are installed above the slab, naturally continuing the construction sequence into the upper structure. The seating structure of the Mercedes-Benz Stadium had to safely accommodate tens of thousands of spectators while providing excellent sightlines. To achieve this, a sloped structural system was installed above the concrete slab with precast seating units placed on top. However, this system had to consider not only the static self-weight but also dynamic loads from crowd movements and horizontal forces. Therefore, the structural components had to be rigidly fixed and behaved as a unified system. To meet the structural demands, the Mercedes-Benz Stadium adopts an in-situ cast-in-place concrete racker beam system to support the seating structure. Though this method is more complex than using precast beams, it allows the rubber, concrete, and formwork to be installed together, forming a monolithic structure connection between the slab, the racker beam, and the vertical columns. The racker beam is inclined at approximately 32 degrees, ensuring that every spectator has an unobstructed view of the field. This slope introduces higher structural demands than typical flat slabs. Diagonal rubber is first installed along the bottom of the beam to resist torsion and diagonal shear cracking, particularly important when bending and shear stresses interact. Next, longitudinal rubber is placed along the beam's length to counter both positive and negative bending moments of up to 1,100 kN, compensating for concrete's low tensile strengths. Finally, horizontal stirrups are installed to encircle the beam cross-section and resist up to 450 kN of pure shear load. Once rubber installation is complete, concrete is cast on sites using vibrators to eliminate voids. This method, integrals are all structural components into a continuous mass capable of distributing complex stress flows uniformly. The completed wrecker beam is designed to safely distribute spectator live loads, vibration, and horizontal forces, while maintaining structural continuity and stiffness across the slab, wrecker beam, and column system. Once the wrecker beam gains sufficient strength, precast concrete seating units are lifted into place by crane. Each unit weighs approximately 12 kN and includes a grout pocket underneath. Loads applied to the seating structure are transferred through the following continuous paths: precast seating, wrecker beam, column, foundation pile, grounds. This continuous load flow ensures that the structure maintains stability under systemic forces, vibrations, and crowd movements. The concrete bowl structure of the Mercedes-Benz Stadium exemplifies a careful coordinate system involving cast-in-place wrecker beams, precast seating units, and high-strength grouted connections. Together, these elements achieve both excellent visibility for spectators and high structural integrity, making it an ideal model for large-scale stadium design. The facade of the Mercedes-Benz Stadium is a triangular steel structure that wraps around the entire stadium. It is not a mere exterior skin, but a structural envelope that resists its own weights, wind loads, and systemic forces. Therefore, each component requires high connection precision, rigidity, and continuity across the entire facade. To meet these requirements, the stadium adopts a diagonal truss system as its facade structure. The facade was not installed using large pre-assembled triangular units, but rather constructed by assembling small vertical and horizontal members on site like a puzzle. First, vertical members were installed to define the initial frame. Then, horizontal members were connected between the verticals to form the triangular geometry. All members were joined on site with bolted connections, and partial field welding was added at joints that required high rigidity. In the earlier stages of construction, when the facade could not support itself, temporary support structures were installed to stabilize the frame until the structure became fully self-supporting. The facade is connected to the main structure through two key systems. In areas with male columns, steel arms from the facade frame are inserted into pre-embedded slots or anchor plates on the column, creating a rigid and load-transferring connection. In spans without male columns, pin columns are used. These are slender vertical steel supports directly anchored to the foundation. Through visual lights, they are designed to safely carry vertical loads from the facade to the ground. The complete facade performs several structural roles: transfers external loads, distributes loads in both vertical and horizontal directions, acts as a secondary support system for the roof and upper structure. By firmly connecting to both male columns and pin columns, the facade allows loads from the roof and upper structures to be transferred continuously down to the building's foundation. As we shown, the Mercedes-Benz Stadium structural system begins with foundation zones adapt to soil conditions, and then rises upper through the mat foundation, male columns, concrete slabs, wrecker beams, precast seating units, and the facade, all interconnected as a part of one massive and continuous structure. Today we have shown these engineered sequences from the ground up, examining how each part was designed and built in harmony. This sequence continues upward into the steel trusses and retractable roof system that form the top of the stadium. We will cover these upper structure systems in our next presentation.